Hi students, today we're going to cover section 6.2, properties of parallelograms. Our goal for the end of this lesson is to use the relationships among sides, angles, and diagonals of parallelograms. So before we get started today, one of the most important things is the definition of a parallelogram itself. So a parallelogram is a quadrilateral with both pairs of opposite sides parallel. So as you can see here, we have a quadrilateral, a four-sided figure, and this four-sided figure has this set of opposite sides parallel and this set of opposite sides parallel. So opposite sides are sides that do not share a vertex. In other words, they are on opposite sides of the figure. And opposite angles do not share a side. So in this case, B and D are opposite angles and A and C are opposite angles, while side BC is opposite to side AD. Our first theorem says that if a quadrilateral is a parallelogram, then its opposite sides are congruent. So in this case we have ABCD and it is a parallelogram. And so we're introduced to this new symbol for a parallelogram. We see it right here. And if this four-sided figure is a parallelogram, then its opposite sides should be congruent. So let's go ahead and prove this. Given the fact that we have parallelogram ABCD, we want to prove that AB is congruent to CD and BC is congruent to DA. Now the diagram that's been included here includes an auxiliary line that connects A to C. And furthermore, the angles BAC, BCA, CAD, and ACD have been numbered 1, 2, 3, and 4. I'm going to set this up as a two-column proof. So on one side I'm going to have statements, on the other side I'm going to have reasons. So my first statement is going to be that we have a parallelogram ABCD. So I'm going to say ABCD is a parallelogram. Now oftentimes you'll see me use the number sign to say parallelogram. This symbol is fairly difficult to draw. So a lot of mathematicians use the number sign to mean parallelogram. So ABCD is a parallelogram and this is given to us. Now, generally speaking, our proofs include four things: definitions, postulates, theorems, and properties. And the first thing that we're going to want to use here is a definition. So my definition that I'm going to use is the definition of a parallelogram. So I'm going to say that BC, segment BC, is parallel to segment AD. And furthermore, AB is parallel to DC. And the reason I can say that those are parallel is by the definition of a parallelogram. And again, I'm going to use the number sign. If I remember this particular Z shape created here by these angles, angle 3 and 1, we can see that these are alternate interior angles, and by the alternate interior angles theorem, angle 3 is congruent to angle 2. So I'm going to say that angle 3 is congruent to angle 2, and furthermore, I can use alternate interior angles also by turning the figure somewhat sideways and looking at it this way, and I can see that Z shape again. And in this case, I can say that also angle 1 is congruent to angle 4. The reason for both of these is the alternate interior angles theorem. And that came from chapter 3. Now if you notice, this segment in the middle, AC, appears in both. So one of the things that we might want to include is that AC is reflexive. So AC appears in both triangle ABC and in triangle ACD. So here, if we include that AC is congruent to itself by the reflexive property, we can show that those two triangles are congruent. So this is by reflexivity. So now I can prove that triangle ABC is congruent to triangle CDA. And remember, with triangle congruence statements, the order is very important. So A is the angle marked green, we go to B, the unmarked angle, to C, the angle marked blue. So for the other triangle, I want to go angle marked green, C, angle that's unmarked, D, to the angle that's blue, A. And we can say this because of angle side angle. Now that we have triangles that are congruent, we can use CP-CTC, or corresponding parts of congruent triangles are congruent, to show that segment BC is congruent to segment DA, and segment AB is congruent to segment CD. Now, a new definition: angles of a polygon that share a side are called consecutive angles. If we think about the word consecutive in English, it means right after each other. So if we were to draw a polygon of any number of sides, so let's think about a pentagon for instance, we have a five-sided figure, two angles that share a side. If we look, this one and this one share a side, they share this side right here, and if you think about them clockwise or counterclockwise, we can see that they fall right after each other. So that's why they're called consecutive angles. And this gives us our second theorem. And it says that if a quadrilateral is a parallelogram, then its consecutive angles are supplementary. So in this case, we start with parallelogram ABCD again, and we can see that A and B are supplementary, B and C are supplementary, C and D are supplementary, and D and A are supplementary. And you'll get the chance to prove this in class tomorrow. Our next theorem says, if a quadrilateral is a parallelogram, then opposite angles are congruent. So if we start with a parallelogram in the previous theorem, we can see, and I'm only going to prove part of this, I'm only going to prove A and C. So I'm trying to show that A and C are congruent. One of the things that I'm going to use is the fact that we have supplementary angles with B. So remembering from the previous theorem, I can say that consecutive angles A and B are supplementary. So I know that the measure of A plus the measure of B equals 180. I also know that B and C are supplementary, so I know that the measure of angle B plus the measure of angle C equals 180. Since both of them equal 180, I can actually set them equal to each other by substitution. So I have the measure of angle A plus the measure of angle B equals the measure of angle B plus the measure of angle C. Well, since the measure of angle B appears on both sides, I can eliminate it using the subtraction property of equality. And so now I have the measure of angle A equals the measure of angle C, and therefore angle A has to be congruent to angle C. So this is a rough outline of a proof of this theorem. To prove that B and D are congruent, we would use B paired with C and C paired with D the same way we've used A and C here paired with B. Let's use the properties of parallelograms in a proof. We're given that ABCD is a parallelogram, and we're given that AK is congruent to MK. So I'm going to start this as a two-column proof. So again, I have statements and reasons. And here again, I'm going to start with my given information. So the first thing I'm given is that ABCD is a parallelogram. That's given to me. And that means a lot of things, but I'm also given that AK is congruent to MK. So two pieces of given information. Now, the fact that ABCD is a parallelogram tells us several things. It tells us that its opposite sides are parallel. It tells us now that its opposite sides are congruent. It tells us that consecutive angles are supplementary, and that opposite angles are congruent. AK congruent to MK tells us only one thing. It tells us that this side, AK, and this side, MK, are exactly the same length. Now, if we look at the overall triangle AKM, we can see because it has AK congruent to KM, that in this case we can use the isosceles triangle theorem to show that A and M are congruent. So that might be the next thing that I would write down. Angle A is congruent to angle M by the isosceles triangle theorem. Now, the fact that this is a parallelogram, remember, that gives us a lot of information. But since we're looking to prove that two angles are congruent here, it would probably be nice to use something that we know about angles. In other words, I would use the fact that A is supplementary to B or A is congruent to C to help me with this. So here I think the best idea would be to use that A and C must be congruent because opposite angles of a parallelogram are congruent. So we have A is congruent to angle C. And again, that's because opposite angles of a parallelogram are congruent. Remember, we don't use theorem numbers, but we can write out a shorthand version of that theorem. Now, if we're super specific here with angle C, so let's go back for a second and let's rewrite angle C in a slightly different way. Let's write this as angle BCD because that is the most specific way to write this. A three-letter identifier, BCD. If we look at what we're trying to do here, we're trying to show that BCD, the angle that we just showed, is congruent to angle CMD. If we identify angle CMD on our triangle here, we can see that that's this angle. And so we can show that the green angle is congruent to this angle by using the transitive property. So in other words, if M matches A and A matches BCD, then angle M has to be congruent to angle BCD by transitivity. And it just so happens here that angle M can be more aptly written as angle CMD. And so that concludes that proof. So our next theorem says that if a quadrilateral is a parallelogram, then its diagonals bisect each other. So again here we have some vocabulary words that keep coming back. Right, we have a four-sided figure whose opposite sides are parallel, then its diagonals cut each other in half. And that's what we can see in our picture. So this kind of question yields an algebra type problem. It says solve a system of linear equations to find the values of x and y in the given parallelogram. What are PR and QS? So in this case we know PR is cut in half by QS. So we know that 3y minus 7 has to equal 2x. And the other equation in this system comes from the other diagonal. So we know x plus 1 has to equal y. When we solve systems of equations, it's best to have an equation that's already solved for one variable. So in this case, I would use the fact that the red equation is solved for y and plug that into the top equation. So if we do that, we have 3 times x plus 1 minus 7 equals 2x. Using the distributive property, we have 3 times x plus 3 minus 7 equals 2x. Combining like terms, we have 3 times x minus 4 equals 2x. Subtract 2x from both sides, add 4 to both sides, and we find that x equals 4. If x equals 4, then y equals x plus 1, so y must equal 5. So here are solutions to this system of equations. So to find the length of PR, we have to plug in the values and solve. Now realize PT is the same distance as TR. So in this case, we could find TR by plugging in 4 as 2 times 4 or 2 times x, which gives us 8. Doubling that gives us the length of PR, which is 16. To find the length from Q to S, we know that y is 5, x plus 1 is 5, so this length has to be 5 plus 5, which is 10. Our final theorem states that if 3 or more parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. So a potential problem might look like this. If the length from E to F equals the length from F to G, equals the length from G to H, and those are all equal to 6, and the length from A to D is 15, what is the length from C to D? So we can see we have 3 or more parallel lines cut off in congruent lengths. These all have the length of 6. It tells us that this whole length from A to D is 15. And it asks us for this length. What is the length from C to D? So we're trying to find this. So we know from the previous theorem that if parallel lines are cut into congruent segments by one line, then it has to be cut into congruent segments with every line. So these 3 pieces have to be the exact same length. If we have 3 parts, or AB plus BC plus CD, and that equals 15 by segment addition postulate, but all 3 are the same, then we know that 3 times the length of CD has to equal 15, because these are all the same. Dividing both sides of this equation by 3, we find that the length from C to D has to equal 5. So all of these are 5. And that concludes section 6.2, Properties of Parallelograms. Don't forget to take the quiz, and I will see you guys tomorrow.